to another episode of the Dark Assassins Podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. We touch on a lot of networking stuff here on the Dark Assassins Podcast, and I've mentioned in the past about wanting to do a dedicated episode or dedicated series of episodes on networking specifically. And, I finally got around to making one, and that is going to be this episode. So in this episode specifically, we're going to be diving in mostly on the hardware aspect of it, like the switches, the routers, the cabling, all that good stuff. Since I know I've talked a lot about switches specifically on this podcast, but we've never really gone in deep into how it works. We talk about networking as this kind of like, hierarchical thing of like it makes, cool things happen and you can do a lot of cool stuff with it. But we never really talk about how it actually works and the infrastructure that is required to make the internet work. And I think once we get into this episode, you're going to really see just how crazy some of these data centers are. Just to make the internet work. But before we get into that, we of course have to delve into the what nerdy stuff have I been up to this week, which really this week, it's more so of a cautionary tale or lesson, if you will, rather than a story time of fun stuff that I was doing. So for all of my software developers out there, I want to speak directly to you for a second. Because as I've mentioned in previous episodes, and any longtime listener of the show will definitely remember, that if you're using a programming language, such as like a C or a C++, that requires you to compile it for each operating system you're building for, we know that just because it compiles on one system does not guarantee that it'll compile on another system. But it goes deeper than that. Oh, yes, it does. Just because your code compiles on another system and runs... So if you say compile your code on one system and you run it on one system and it works fine, and it compiles on a different system, that does not mean it'll work fine on that other system. So I realized, well, I guess I kind of knew that already, but I rediscovered that the hard way when I was working on the C++ game that I've been working on, and I've been trying to make it cross-platform, and I realized that the graphics library that I'm using got updated. And the reason I'm not using the built-in C++ graphics library is because it doesn't exist. So I had to get one, an open source one that I found online. It's called Raylib if you're interested in checking it out. And I saw they released a new version, 4.2. I was using 4.0, so I downloaded the new libraries, the new source files that I needed. And of course, to make sure that the graphics was actually working, I loaded up the graphics tests and used those to make sure that the graphics were still working. Well, apparently when I was testing the graphics initially, which I haven't touched the graphics in a while, when I was doing the graphics initially, it was building and compiling fine on all my machines, and it was running fine on my Mac, and I was like, cool, everything's great. Well, everything's not great because I spent probably an entire day thinking that something with the library configuration was wrong. Nope, just turns out that the compiler, while it compiled the code perfectly fine, whenever I tried to run it, it would crash. So that's been very fun trying to debug. I'm still in the process of trying to debug it as of the recording of this podcast. But let this be a lesson for all of my new and young software developers out there listening, and a reminder for all the veterans out there that have been doing it for a while. Just because your code can compile on a machine does not guarantee that it'll compile on another machine. And just because your code can run on one machine does not mean that it'll run as you expect on another machine. Lest if you don't test your code often on every machine you're trying to build for, you become the, well, it works on my machine kind of guy. And nobody likes the it works on my machine guy. So don't be that guy. So test your code often. Or you could just use a language like Java or something that only requires you to compile it once and it'll work across all the machines. But hey, sometimes that's either not an option, or sometimes you just want to do it, not use Java and use something like C++ because you can, or you just want your code to be optimized, fast, and be able to manage the memory yourself. But anyway, that tangent aside, let's get into networking, because this is going to be a chunky episode as far as lengthwise, I would assume. So the first thing that I want to talk about is NICs, or network interface cards. So any device that can connect to the internet has one of these in them. So so this can be anything from your computer to your phone, tablet, smart TV, whatever. So most commonly, this is recognized as an Ethernet port, which is most commonly recognized as the RJ45 connector, which the best way I can describe this without actually having a picture of it for you is it's that port that kind of looks like a house, sort of, or maybe an upside down house, depending on how it's oriented on the back of your computer or on the back of the router or the side of your laptop if your laptop has one. But it's basically, it doesn't matter if it's a wired connection like Ethernet or Wi-Fi, it's all the same. Basically, that either wireless or wired signal gets sent to a dedicated hardware component, either on your logic board or on an expansion card, like if you're using a PCI expansion card for your networking. And then that integrates with your system to allow for network connectivity. So these network interface cards, they work on the physical and the data link layer. So kind of as you're going to see, while we're focusing mostly on hardware in this episode, there are parts that aren't specifically hardware that we kind of have to touch on because they're kind of intermingled. And then eventually, whenever we talk about other parts of networking that isn't hardware related, we're going to have to do the same thing, but in reverse, and kind of touch on some hardware aspects because how closely tied they are. But speaking of the OSI model, so there's basically two models when it comes to networking. There's the OSI model and the TCP/IP model. Now, they're essentially the same exact model. The only difference is the OSI model has 7 layers, while the TCP/IP model has 5. But the TCP/IP model really just takes the top 3 layers of the OSI model and condenses them down to 1, because that's essentially all it is. So when we're talking about OSI model versus TCP/IP model, just know that they're basically the same thing. And the reason why they're called layers is because if you look at how data packets or network packets are structured, they're basically built on each other. So the physical layer gets built upon by the data link layer, which then gets built upon by the network layer, and then so on up the chain. And then it's the same in reverse once it's going down the chain all the way down to the data link or to the physical layer. It's basically going in reverse, stripping those layers of the network packet off, so the respective devices or applications know where to send respective data. So that's kind of what we're talking about when we're talking about the OSI model. So the physical layer is just, the ones and the zeros, the binary data that's being sent. And the data link layer is how your data packet gets sent from you to your destination And if you've heard the term MAC address, I believe we've talked about it on the podcast before. That's where this comes in. Every network interface card interface, I guess, if you will, has a MAC address. So if you have a desktop that has Wi-Fi and an Ethernet port on it, it'll have a MAC address for the Wi-Fi network interface and a MAC address for the Ethernet interface, and those will be separate MAC addresses. And the reason this is important is because, as we'll see, the MAC address is really important when it comes to sending data to your machine so it knows where it's supposed to be going. So the MAC address is kind of like the name of your computer, and the IP address, which is the network layer, is kind of like your computer's physical address. Now, an analogy we can use to kind of talk about this is if you want to be old school and you want to send a letter in the mail, you could put the address, just the address, and it'll get to the destination, no problem. But say if you sent that letter to your friend who has, say, 2 other roommates, if they just get a letter with their address on it, they won't know who it's supposed to go to. So that's where the MAC address comes in. If you put the MAC address on it, or in this case, your friend's name, then when it gets to their house, if one of their roommates picks it up or your friend picks it up, they know that it's supposed to go to your friend. So that's kind of how the MAC address plays into this. Now, you might be thinking that maybe like my phone or my desktop either only has an Ethernet port or only has Wi-Fi capability, so it only has one MAC address. Wouldn't it be kind of redundant to have to specify the MAC address if there's only one IP tied to one MAC address? And technically, you're not wrong, but there are instances where you could have multiple ports tied to the same IP address. So if you think of it like if you live alone, if you live by yourself, yeah, anything sent to your house is obviously meant for you, unless the instance where the previous person that lived in your house hasn't fully switched over their mail yet and you're still getting stuff that's supposed to be for them, which, definitely happens. But in an ideal world, anything that's sent to your house is meant for you. But like I mentioned, there's ways that you can combine multiple ports together to send on one IP address, and this is called link aggregation. And this allows multiple Ethernet ports to share the same IP address, and this basically allows those Ethernet ports to work in parallel, so you can increase the throughput of your total connections rather than having single connections. So basically what this means is if you have a server that's connected to a gigabit switch and you use link aggregation and your server has 4 ports on it, there are 4 Ethernet ports on it, you could do link aggregation on all those 4 ports. So rather than your server only having the ability to handle 1 gig of throughput through each one of those ports, it can handle 4 gigs of throughput. And it can be evenly distributed across all those ports. So this is kind of definitely better used in like the data center realm where they're dealing with, as we'll get into, massive amounts of gigabit. And if you have a network interface card with say like 2 or like imagine if you have a network interface card with like 2 ports or even 4 ports, and you're talking like 40 plus gigabit speeds, link all those together, you got some very fast speeds, and you can handle a lot more data. So that's kind of the point of link aggregation there. So then if we go back to the roommates example, this is where if you have multiple roommates and you don't have the MAC address, they don't know where it's supposed to go. So that's kind of how network interface cards work. And now kind of going up a step, we have routers. Now, if you got your router from your ISP, it's a lot more than just a router, I'll say that. It's basically a jack of all trades device. So it's basically a modem, a router, an access point, and a switch all in one device. Now, the only caveat to this is if you have, say, like fiber or an Ethernet drop directly to your house and you don't have the old school coax cable that comes to your house, then you probably don't have the modem aspect. But otherwise, you got all of those. And even if you don't have the modem aspect, you still got the router, access point, and switch aspect all built into one. Which in fairness to the ISP router, modem, access point, switch combos, most routers that you could buy, like, off Amazon or Walmart or Target or wherever, or Best Buy, most of those routers are going to have, a switch built in with multiple Ethernet ports, and it's going to give you Wi-Fi access in addition to being your router. So that's not necessarily uncommon, but you can, get all these devices separately if you want to. But breaking down how it's all those things in one device, obviously the modem is what converts that coax cable signal into Ethernet and back. And then it also provides Wi-Fi to your house, so that's the access point aspect of it. And then it's got multiple Ethernet ports on the back of it, which, basically acts like a network switch. Now, obviously, like I said, you can have all of these as separate devices, but the average consumer just wants the Netflix to work, and having to tinker around with 3 or 4 devices, that's way too much work. Plus, from the ISP's perspective, it's just kind of cheaper to lump it all in one rather than having to supply you with a modem, a router, an access point, and a switch. It's definitely cheaper on their end just to give you one device. And it's easier for them to manage, too. Easier for them to manage just one device rather than 4 or 3, depending on if you have a modem or not. Now, the router, unlike the network interface card, the router works on the network layer, so it's dealing with the IP addresses. So the router is in charge of making sure that your network packet gets to where it's supposed to go, even if the destination is on a different IP network than yours. And when I say a different IP network, this is talking about subnetting, which, not to go super in-depth on what subnetting is because that's its own separate topic, but subnetting is essentially just a collection or a range of IP addresses. And you can think of it kind of like a neighborhood. It's basically like a neighborhood is a collection of houses that are kind of close to each other in a subdevelopment. That's basically what a subnet is for IP addresses. It's a collection of IP addresses all next to each other. And similarly, like housing developments can be pretty small or they can be pretty large. Same thing goes with subnets. They can be pretty small or they can be pretty large. So if you're trying to send something that's on your IP network or on your subnet, you don't necessarily need the router for that because that's all like data link layer stuff. Just like if you're in your neighborhood and you want to give something to your neighbor, you don't have to give it to the post office. You can just, walk it to your neighbor's house and deliver it to him yourself. Which, speaking on that, just because so obviously, if you want to send something to your neighbor, and you can obviously put it through the post office and it'll get there all the same. Just like if you want to send something on your network, you could send it to the router and it would send it, to the right place all the same. But obviously, if you wanted to send something to your aunt who lives across the country, you can't feasibly do that yourself. So that's where you have to send it to the post office and they will route your letter to your aunt. Yes, that was a terrible pun, I know. But at the end of the day, the job of the router is just to forward traffic to different networks. Now, I'm going to use this mail analogy a lot throughout this episode. So think of the router as the post office is basically what I want you to think about as we're going through this. And it'll make things make a lot more sense. Now, the real question is, what magic voodoo is the router doing to send your network packet from here to, wherever on the vastness of the interwebs that you're trying to send it to? So basically, your router keeps a table that tells it where to send packets to. So in cases of, and the other thing with the router too is, like the post office, it's always forwarding packets, whether you're sending data out or not. It's always forwarding packets. So how it does this is it has a table, and it also has algorithms as well, which help determine where it should be sending those packets to. So when your router receives a packet, first, what it does is it checks the IP address of the destination. So in a network packet, it'll have the destination address as part of that whole packet. So the router can peel that part off and see what the destination is. And if the destination is not the IP address of the router, then it knows it has to forward that packet onwards to wherever the next hop is. So the way it determines that is it does a lookup on its table and then finds a match with the longest prefix. So what this means is, if, say, your router has two prefixes in it, one is 10.3 and one is 10.3.23, and it receives a packet with the IP address of 10.3.23.10, it'll forward that packet that it received to wherever the entry tells it to forward packets for the 10.3.231. So that's basically how it does it. So if we go back to the post office example on this one, say that the post office is located in Memphis, Tennessee, and it receives a mail dump from the post office in Nashville, Tennessee, and it sees that it got a letter that's destined for Austin, Texas. So what that post office in Memphis is going to do is it's going to forward that piece of mail that's meant for Austin, Texas, to the next post office in the direction of Austin, Texas. So say, Little Rock, Arkansas or something. Maybe that's the next hop. So it'll, basically what it does, it looks in its table, sees the closest match along the path, and then forwards it on to there. Now, what if the IP address for the destination is the IP address of the router? Well, that's where NAT, or Network Address Translation, comes in. So let's give a hypothetical example here that your router has an external IP address of 70.131.206.185. Don't worry, you don't need to remember that. There's no quiz at the end. Or is there? Just kidding, there's not. But basically, if you want to actually find out what your global IP address, what you can do is, in whatever your search engine of choice is, if you search "what is my IP," you'll get your global IP address. Unless you're using like a VPN or a proxy, then it's going to be different. But for the vast majority of you, if you just search "what is my IP," that's going to be your global IP. But if you are using a VPN or proxy and you search "what is my IP," that's what the search engine thinks your IP is, even if it potentially isn't. But that's kind of, getting sidetracked here. So if all of the outgoing connections to the internet are basically showing your global IP, then we need to figure out, how does the router know where to send that packet to? Because unless you live by yourself and only have one device connected to the internet, you're probably going to have more than, multiple connections going out and packets coming in that are meant to go to multiple devices. So the way that this is done is, if you're on like a Windows machine, if you type either in the command prompt or PowerShell ipconfig, or if you're on a Mac, you type ifconfig, or if you're on Linux, you could type either ifconfig or IP space address. You'll see an address there, which is different from the global IP address. So remember, that global IP address was that 70.131 thing. Your local IP address is most likely going to be something like 192.168.1.30 or something like that. And that's basically the network address translation denoting your LAN, or your local area network. Now, as far as the internet's concerned, the broader internet as a whole, your local IP address, as it's called, that 192.168.1.30 number, that IP address doesn't exist. That's just for, local devices on your local network to be able to talk to each other, and for your router to know where to send data to. So with that out of the way, let's get back to the question of how your router uses network address translation, or NAT, to be able to forward the packets to where they're supposed to go. So the router keeps a table. It keeps a network address translation table, and this table contains the ports of the origin port that your machine sent out, as well as a doctored port that it sent out to the broader internet, as well as your local IP address. So basically what this allows you to do is allows you to have 5 devices all going to different places on the internet with the same global IP, and you don't mistakenly get the video stream your mom's watching, and your mom doesn't mistakenly get the website that you're trying to go to. So it works pretty well. So here's an example of it. So say you're trying to reach out to Wikipedia, since you're doing research on something. And then you reach out to Wikipedia through the source port of 10,546. Obviously, Wikipedia is outside of your home network, so you have to go to your router first. So when the packet gets to the router inputs your local IP address, so that, 192.168.1.30 number, as well as the source port that you reached out on. So that would be that 10,546. Now, once that happens, what your router does is it doctors up the packet. So basically, it changes the source IP address to whatever your global IP address is. So in our case here, there was that 70.131 number. And then it makes a different source port to send the data out on. Now, before we continue, some of the keen eye among you might be saying, oh, but wait a second. Wikipedia uses HTTPS, and HTTPS uses port 443, not 10,546, you dum-dum. Which, technically, yes, you are correct. HTTPS does use port 443. However, that 443 port only matters as the destination address, not the source address. The source address can be whatever the heck you want it to be. The destination port only matters when you're trying to connect to a service, not when you're, identifying the source port. And the reason why this works is if you're running your own web server with HTTPS, if you try to connect to any web request with HTTPS on, that 443 port, you're going to have issues because you're already binding that 443 port to your web server. So you're going to run into problems. But even that aside, if every time you tried to reach out to a website on the same port 443, you would be in all kinds of trouble, because if you reached out to, say, Wikipedia, and then you reached out to, say, Facebook, both on 443, you're going to have all kinds of conflicts because you're trying to access, different data on the same port. And then if everyone on your network is trying to do the same thing, your router is going to have no idea where the heck to send the data to. So that's why the source port is generally a higher number that's outside the standard port ranges for generic services. So like it's outside the SSH port, which is port 22, outside the HTTP port, which is port 80, outside the HTTPS port, which is port 43. It's way up there, so it doesn't interfere with things like that. So the only reason why the only way that the source port matters and is applicable is on the server side. So when a server receives a connection, it knows what port to send the data back to. But as far as the client side, when you're trying to reach out to a service, that's where the destination port matters. But the source port can be whatever. The source port is mainly for the server to know where to send the data back to, essentially. So now back to our example. So after the router doctors up the packet, changes the IP address and the origin port, it puts that new port that it generated in the NAT table with your local IP and the original port that you tried to reach out on. So then when Wikipedia responds to you, it'll send the response to your global IP, which is your router, with that port that it doctored up, which in this case, let's say, is 32,451. So it sends data back to IP address 70.131.206.185 on port 32,451, and then your router gets that data, and then it looks at the port that it came in on, so that's the 32,451, and then it does a lookup in the NAT table and sees that that port is mapped to your IP address, which is the 192.168.1.30 on port 10,546. So that is where your router sends the data to. And that's basically how network address translation works in a nutshell. So your router doctors up some data for you on your behalf, adds that data to its network address translation table as a lookup, and then that's basically how it knows where to forward data to when you have, say, 5 different devices all on the same network browsing the internet at the same time. So pretty cool stuff. Now, to really hammer home this mail analogy, so if none of that nonsense with all those numbers, if none of that made any sense to you, hopefully this will make some sense. So you can think of your zip code as your global IP address, because when the post office is trying to send your mail to you, they're basically just looking at the zip code to know where to route that letter to go to the correct post office. Similarly for the router, if your router receives mail that doesn't have its IP address, it then forwards it on to wherever it's supposed to go next in the chain, just like a post office would. Now, your street address and your house number are kind of like your local IP and the source port respectively. So your local IP is kind of like your street address, because it's kind of like a broad scoping thing, because you could have multiple connections to multiple different internet sites at the same time, all going to the same local IP address. So you need to know what that source port is to be able to direct it to the right port, so it goes to your right application, so you view it where you're supposed to. Because it'd be kind of weird if you had an SSH terminal open and just out of the blue you got a bunch of HTML data flowing through there from your web requests that you were doing in your web browser. That'd be kind of weird. So that's where the house number comes in. So the house number is kind of like the source port. So once the mail truck gets onto your street, it knows which house or in our case, which port it should send that data to. Now, then the last thing is the MAC address, which, as we've mentioned before, the MAC address is like your name. So if you have multiple network interface cards with the same IP address, it can go to the right one. Just like if you have multiple roommates and the letter has your name on it, it's supposed to go to you rather than one of your roommates. Hopefully that made some sense. If not, shoot me an email, contact@darkassassins.com. Tell me I'm dumb and I don't know what I'm talking about and I can't explain anything. By all means. So next up, next is kind of I don't know if you could say inspiration, but one of the reasons that I've wanted to make this episode, and one thing we've talked about a lot but I never really dove into, and that is switches. So there's really, well, I guess technically there's more than 2, but there's 2 main types of switches, and then there's like a variety of each kind. So the 2 main types of switches, as I believe we mentioned before on the podcast, is managed switches and unmanaged switches. But before we get into that, the main way a switch works is it basically kind of works like a router, except rather than working on the network layer with IP addresses, it works on the data link layer with MAC addresses. So what this but a switch in general just allows you to connect multiple devices to the same network. And another thing you can do is have PoE on a switch, which is power over Ethernet, which we'll discuss in a little bit here. But the one thing you have to keep in mind if you're trying to look for PoE is PoE switches are always more expensive than just normal switches because they'll obviously have a lot of extra features, as we'll get into. But specifically, when we're talking about unmanaged and managed switches, the unmanaged switches are essentially dumb switches, which are just plug and play. There's no configuration, no nothing. You plug your cable in and you're connected. Now, managed switches, this gives you a lot more manual control and configuration over how and where data goes. So managed switches generally have the ability for you to configure them either through a serial, a command line, or a web interface. You can configure all kinds of stuff, like you can prevent looping with the spanning tree protocol. Now, basically how a loop works is essentially if you have a device with one or more active paths to the device. So say, for example, if you have a device that has both Wi-Fi and Ethernet, and it has both its Wi-Fi and Ethernet connected to the same network, that would cause a loop. So the point of the spanning tree protocol is to prevent loops and detect loops and stop them from happening. And the reason is because by doing this and removing the loops, it prevents excess broadcast traffic. And broadcast traffic is essentially traffic that's sent to all the devices on the network. So an example of this is we've talked about Wake on LAN before on the podcast when we were talking about lights out management and remote management and all that good stuff. Now, Wake on LAN is specifically a data link layer is a data link layer thing. So basically, well, I guess not, it's technically network layer. But basically what it does is it sends a blast to the broadcast address to the specific MAC address telling it to wake up. So that's an example of a broadcast address. So if you had a loop or even multiple loops, that could, cause a lot more congestion than needed with the kind of the broadcast going to the same place in, multiple different ways. So that's kind of the point of the spanning tree protocol, is to prevent that from happening. Now, another thing that you can do is you can also manage port bandwidth. So if you say were running, like if you're running your own ISP, for example, and you knew, or you were, if you were a parent and you wanted to be cruel to your child and you had their desktop hooked up to your switch and you wanted them to have pleb internet and only be able to get, say 100 megabits to your server rather than a full gigabit, you could go in there and manage the port that their desktop's hooked up to if you wanted to. But more specifically, a more realistic case for this I could see is if for example, college campuses, when all the dorms have an Ethernet plug to them, darn well you ain't getting gigabit off that thing. You're getting some very, very slow speeds. And the way they can do this is they can, manually set the speed limit essentially for the ports on the switch because it's managed. Another thing you can do on a managed switch is you can create and modify VLANs, which we've talked about before. Basically a way to segment up your network. So only certain devices connected to certain ports can talk to each other, but not others. Another functionality you can have is port mirroring, which essentially what this does is it forwards the data like normal, but then also sends a copy of that data to either a log or to some other device. And then it can also do MAC address filtering, which can limit network access to certain devices based on the MAC address. And basically, the whole point of a managed switch is for those that really want to dive into networking and take control of their network and, tinker with it and mess around with it. But as we mentioned before, managed switches are more expensive than unmanaged switches because obviously you have a lot more functionality. But since we've been talking about switches, we also mentioned PoE, or Power over Ethernet. So what does that mean? So Power over Ethernet, as the name suggests, is a way to distribute power over an Ethernet connection. And we're going to get into Ethernet here in a little bit. But basically, in order to have power over Ethernet, you need a compatible switch to do this. And then there's also multiple variants of power over Ethernet. But some use cases for why you would even want to use power over Ethernet is it's really useful for things like running wireless access points, or if you have a Raspberry Pi, you can get special power over Ethernet adapters that kind of plug into the GPIO pins on it. So you don't have to worry about carrying the extra power cable around. You can just plug the Ethernet in. And also IoT devices. So like I kind of mentioned with the Raspberry Pi, the benefit here is you only have to run one cable to the device, and that gives it not only internet connection, but also gives it power. So one way where this is really useful is if, say, you're running security cameras outside, having to find a power outlet for a security cam outside, that could be one kind of a pain to find. You could potentially have issues if it rains. And if you're trying to find an outlet inside, that could be kind of hard to have a long enough power cable to route it there. So if you just have power over Ethernet, you can just run one cable, which is the Ethernet cable, plugs right in. Plus, personally, in my opinion, it's a lot cleaner of a setup because generally, power over Ethernet devices are generally high up. Like if you have an access point, for example, it's generally on the ceiling, and your power outlets are generally not. They're generally closer to the floor. So having this, nice, beautiful access point mounted on the ceiling, and then this black wire running over on the ceiling and down and plugging into the power outlet isn't exactly the cleanest solution. So it'd obviously be a lot cleaner if you can just have, one single Ethernet cable that can plug in, and then you can, route it through the ceiling or whatever. Obviously, I guess you could do the same with the power cable, but that's kind of a lot more work. So having power over Ethernet's just kind of a nice feature to have. So I mentioned there's different standards of power over Ethernet. So there's PoE, PoE Plus, and then PoE Plus Plus. Very unique naming scheme for sure. So PoE is able to supply 15.4 watts at the port, but realistically, once you actually get to the device itself, it's more like around 13 watts. And this requires at minimum a Cat3 cable, which we'll talk about what that means here in a little bit as well once we talk about Ethernet. And then you have PoE Plus, which is 30 watts max at the port, but realistically like 25-ish once you actually get to the device. This requires Cat5. And then you have PoE Plus Plus, which is 60 or 100 watts depending on the version. There's kind of like two versions of PoE Plus Plus. So 60 or 100 watts at the port, but that really translates to like 51 or 71 respectively at the device. The cool thing about PoE Plus Plus, though, is it actually supports 10 gig connections, so that's pretty cool. And it requires a minimum of Cat5 like PoE Plus. Now, obviously, if PoE on a switch is expensive, PoE Plus is even more expensive, and PoE Plus Plus is even more expensive than that. And also, if you have a switch with PoE, it's most likely it's at least probably going to have a fan in it, almost certainly going to have a fan in it. And it's going to be louder than just a regular switch, mainly because if you have power being outputted, that's heat, and you need to cool it down, so you use a fan. So if you have like one of those big boy enterprise switches with like some kind of PoE on them, I've heard stories that those things make rack-mounted servers sound quiet. So something to keep in mind if you're ever looking at a PoE switch. You definitely want to make sure you do your research on it. But we've talked about Ethernet. Now, what is Ethernet? So generally speaking, it's described as hardwiring networks through twisted pair copper cables that terminate in the RJ45 connector, which is that kind of house-shaped thing we talked about earlier. Although it's not specifically restricted to copper twisted pair cables, as we're going to kind of see, there's kind of sort of a transition to fiber optic cables, which can transfer the same signals as a twisted pair cable can. And once you really want to get to the fast speeds, you really can't do it over the twisted pair copper cables. Although the twisted pair, just regular Ethernet cables, those are still reign supreme in the home space, mainly because pretty much anything that you would want to run cabling for at your house, you could probably do with just standard Ethernet cable. You don't really need fiber optic cables to do that. Now, when we talked about CAT, what that means, it's kind of funny. That's just short for category, actually. So twisted pair cables come in different varieties, which are called categories, or CAT for short. Now, there's more. As we mentioned, there was a CAT 3, but realistically, the cables that you're going to see is CAT 5, CAT 5e, CAT 6 and 6a, CAT 7 and 7a, and CAT 8. Now, really, the main differences between these is the speeds in which they can transfer data and the distance that they can transfer data. So going through these real quick, Cat 5 can do 100 megabits per second and a gigabit per second, up to 100 meters. Now, one thing I want to mention as we're going through the different variants of CAT cables, all of them are backwards compatible with each other. So if I say, for example, this next one, Cat 5e can do 1 gigabit per second and 2.5 gigabits per second at up to 100 meters, it's also able to do 100 megabits per second and a gigabit per second. So it's not just limited specifically to this range. I'm just giving the upper end, basically what's new in the cable, I guess you could say. So going on from there, we have Cat 6, which can do 5 gigabits per second and 10 gigabits per second, but that's limited to 55 meters rather than 100 meters of the previous one. And then Cat 6a gets the upgrade of doing the same 5 gigabits per second and 10 gigabits per second, but can do the up to 100 meters. And then Cat 7 and 7a is the same 5 gigabits per second and 100 gigabits per second up to 100 meters. And then Cat 8 can do 25 gigabits per second and 40 gigabits per second, but only up to 30 meters. Now, I mentioned that Cat 7 and 7a and 6a are basically the exact same, so what's the difference? The difference is the Cat 7 variants have more shielding on them, and basically what this allows it to do is it not only makes the cable thicker, but it also makes it less resistant to potential interference. And also, if you're trying to terminate your own cables, it can be harder to do that because the cables are thicker and have more shielding on them. But realistically, if you're trying to set up a home network, I think Cat 6 is kind of the sweet spot, or Cat 6 or Cat 6a, because it gives you up to 10 gigabits per second, and it's cheaper than Cat 7. And Cat 5e, while it can give you, and Cat 5 for that matter, can give you a gigabit per second, if you ever down the line want to upgrade to say 10 gig, then you're going to have to get new cabling. Although you might be getting new cabling anyway, as we'll kind of get into, but you at least have the option to use the same cabling, I'll say that. So that's, I said you might have to get new cabling. Speaking of which, we have a different type of connector, which is different from the RJ45 connector, and that is the SFP connector. Now, SFP just stands for Small Form Factor Pluggable, and this is another variant of Ethernet, and its connector kind of looks like a rectangle. So if you see a network switch with kind of rectangle ports on it, those are SFP ports. Now, in order to connect to these SFP ports, you have to have what are called SFP transceivers, which is basically able to convert the signals for whatever type of cable you're using, whether you're using fiber or some type of copper cable, whether that's a standard RJ45 Ethernet cable or a DAC or a direct attach copper cable, as we'll talk about later. You have to have some kind of transceiver to be able to plug into that SFP port. Now, there's different types of SFP, but before I get into that, a little bit more on the transceivers here. Why you potentially would, I believe we talked about this when I talked about what the heck is up with 10 gig. But the reason why you might want to be upgrading your cables anyway, if you do upgrade to 10 gig, is while you can get transceivers that are made for RJ45, they're more expensive than just either direct attached copper cables or transceivers for fiber cables. And not to mention the network interface cards specifically for RJ45 connections are more expensive. So while you might not necessarily need to upgrade the cables, you're paying for that convenience elsewhere. So it's kind of a trade-off on what you want to do. But because SFP also allows for fiber connections rather than just the twisted pair copper, this allows for much faster speeds, as we'll shortly see. So let's run through this beautiful alphabet soup that is the different types of SFP connectors, at least as of the recording of this podcast episode, because SFP is not strictly regulated to the data center, but it's pioneered in the data center. So the data center is always growing and evolving and getting faster and faster. So who knows, maybe by the time this episode goes out, there'll be another new version. I don't know. But as of the recording, we have SFP, SFP+, SFP28, QSFP+, QSFP28, SFP56, QSFP28, SFP-DD, QSFP56, and QSFP-DD. Now, I have a feeling that a lot of you heard that and were like, what the heck is all of that shenanigans? What is that alphabet soup craziness? And I don't blame you, so let's break it down. So SFP is essentially the OG. It was the first one. It can do a gigabit per second over fiber or, your standard RJ45 twisted pair copper with a minimum of Cat5 or greater. And then we have SFP+, which is backwards compatible with SFP and can do up to 10 gigabits per second over fiber, twisted pair with Cat6 or greater, or a DAC, or direct attached copper cable. Then we have SFP28, which is backwards compatible with both SFP and SFP+, and can do up to 25 gigabits per second over fiber, twisted pair with Cat6/8, or a DAC cable. And then we have QSFP+, which doesn't have any backwards compatibility with the ones we've mentioned previously. But what you can do is you can split that QSFP+ port into 10 separate 10 gigabit ports, or essentially 10 SFP+ ports, which is kind of where the Q comes from. The Q stands for quad, so quad SFP+. So essentially 4 kind of joined to 1. Now this quad SFP+, because it's essentially a combination of 4 SFP+ ports, can do up to 40 gigabits per second over fiber, twisted pair with Cat8, or a DAC cable. And then we have QSFP28, which, as you might be able to guess, it can do up to 50 gigabits per second because it's a combination of the SFP28, which kind of, I guess one thing that is weird is it's a Q, but it isn't technically quad, but it is backwards compatible with QSFP+, but this only works with fiber or DAC cables, and this can be split into 2 separate 25 gigabit ports rather than the 4 that the QSFP+ could do. The QSFP28 can only be split into 2 ports, but they can both be 25 gigabits per second. Then we have the SFP56, which is backwards compatible with SFP, SFP+, and SFP28, and it can do 50 gigabits per second over fiber and DAC cables. And then we have QSFP 56, which is backwards compatible with QSFP+, and it can do up to 100 gigabits per second over fiber and a DAC, and can be split into 4 separate 25 gigabits per second ports if you so choose. And then we got SFP-DD, which currently isn't in use, but it was essentially, as we'll talk about QSFP-DD, it's basically that version, but the single kind, I guess you could say. So it's backwards compatible with SFP, SFP+, SFP28, and SFP56, and it can do 100 gigabits per second over fiber or DAC cable. And then we have QSFP56 here, which is backwards compatible with QSFP+, QSFP28, and it can do 200 gigabits per second over fiber or DAC cable, and can be split into 4 separate 50 gigabits per second ports. And then finally, we have QSFP-DD, which is backwards compatible with QSFP+, QSFP28, QSFP56, and can do 400 gigabits per second over fiber or DAC cabling. And it also can be split into 8 separate ports of 50 gigabits per second as well, just to put some icing on the cake. So you might be wondering kind of what's the difference between SFP and the QSFP variants. Now, aside from the speed, backwards compatibility, and the Q variants being able to split into smaller variants, essentially, the other difference is the Q variants are slightly wider than the SFP variants. So the SFP variants is like a smaller rectangle, almost square-like, and then the QSFP are wider. I guess kind of makes sense since, you're fitting essentially multiple channels in there to be able to, split off into, subsections, but that's basically the difference. Now, here at the Dark Assassins podcast, we believe that context matters. So you're probably wondering what all this means. We talked about a lot of numbers, gigabits per second, a lot of different variants of that. But what does any of that mean? So I'm here today to provide you context. So back in college, me and my friends like to compare our internet speeds by determining how fast, which I guess more accurately since we were in college, how slow it would be to download GTA 5. So GTA 5 is going to be our benchmark for these speeds. So GTA 5 is about 95 gigabytes in size. Now, for this speed comparison, we have to make some assumptions here. So we essentially are assuming perfectly optimal conditions with no bottlenecks whatsoever. So this means there's no slowdown in network speeds. There's no processing on your computer that makes the speed of the download go slower. You're able to write at the speed that you're downloading at, which, for context, I don't know if there's really anything consumer grade that can write at 400 gigabits per second, but it is what it is. I guess if you had super duper fast RAM and you had enough RAM, you maybe could have it saved all to RAM and then moved over to disk later. I don't know. But for the sake of this, we're just assuming that everything is optimal, everything works perfectly, there's no bottlenecks, no nothing. So with that in mind, my college dorm had 30 megabits per second. Now, personally, I think that's kind of generous. It was generally a lot slower than that, but assuming that 30 megabits per second internet, it would take 8.5 hours to download GTA 5, which kind of makes sense because from what I recall originally downloading it, it was a start the download, then go to bed, because I think it was 12 or 13 hours is what Steam was saying it would take to download. So it's kind of in the same ballpark if you factor in, various network slowdowns and bottlenecks and, real world stuff. That's kind of about accurate. Now, let's take the average home internet speed of someone in the United States. Now, generally, from what I could gather, that's around 100 megabits per second. You obviously have the people that are more urban that have, the the gigabit speeds and, the much faster speeds. And then you have the people out in the middle of nowhere that have, the satellite internet that get like maybe 25 megabits per second. So average it out, sort of 100 megabits per second. We're just going to go with that. So if you had that internet speed, it would take just over 2 hours to download GTA 5. Now, if we get into the SFP realm with these speeds, at 1 gigabit per second, it would take about 12 minutes to download GTA 5. So, pretty quick compared to the 8.5 hours for the 30 megabits per second and the 2 hours for the average home internet speed in the U.S. Now, if we move up to 10 gigabits per second, that would take just over a minute. So we're getting pretty quick here. 25 gigabits per second would take 30 seconds. 40 gigabits per second would take about 20 seconds. 50 gigabits per second would take 15 seconds. 100 gigabits per second would take 7 seconds. 200 gigabits per second would take 3 seconds, and 400 gigabits per second would take 1 second. Could you imagine downloading all of GTA 5 in 1 second? That's kind of mind-blowing to me. Like, there'd essentially be no progress bar at all. Like, you would hit download and it would be done. Like, obviously assuming that, everything was perfect and there was no hiccups or slowdowns or anything like that, which realistically there would be, but for the sake of argument, say there isn't, that's kind of insane. So for all those plebs out there talking about their 10 gig switches that they got in their house, they ain't got nothing on these data centers with 400 gigabits per second, let me tell you. So my 400 gigabit switch is coming in next week. I will update you when that comes. Just kidding, I don't have that kind of money. But you might be asking yourself, who would need speeds that fast and why? Now, my answer to that is a very good question, but answer me this. Why not? Like, why not have speeds that fast? Because you can. That's why. Now, on a serious note, it really comes down to how much data you can transfer and route. So if we think of the average internet speed of around 100 megabits per second, if you multiply that up by how many people there are in America, which, I don't know, it's in like somewhere like over 300 million, I think. So that's a ton of data. So, and that adds up super fast. So you need to have a pipe big enough to be able to have all those streams of 100 megabits per second to be able to handle all of that. So let's say if hypothetically you had a 1 gigabit per second pipe, you could handle 10 simultaneous streams of that 100 megabits per second before any kind of bottlenecks or slowdowns happen. And this is because if you tried to have more than 10 streams, then you'd be trying to cram more down the pipe that can actually fit. So you would need a bigger pipe. So the big reason why these data centers are, getting these faster and faster speeds, which are essentially ludicrous to us, normal people, is because, they're basically the backbone of the internet, right? They're hosting the services we use. They're hosting the routers and switches that route our network traffic. And if they didn't have beefy infrastructure, our internet would be slow as heck and we'd be complaining all the time. So it kind of pays that they have, this big infrastructure. And with home internet speeds getting faster and faster, and with the implementation of 5G, the super fast, perfect, massive speed increases, at least under perfect circumstances, which, hot take, the majority of 5G that you're going to get is just rebranded LTE. But, it's a separate discussion. But for all these faster speeds that are coming to the mainstream, you obviously need a lot of horsepower to be able to handle all that, which is where these high-speed connections come in and why you need bigger and bigger pipes and faster SFP connections. Now, to kind of put this into context with a more real-world scenario, if you imagine like a plumbing infrastructure, if you're trying to accommodate plumbing for 1,000 people, that's going to look a lot different than accommodating for 100,000 people. Because if you say you accommodate for 1,000 people, if maybe that number increases to 1,500, that's probably not too big of a deal since not everyone's going to be using the plumbing at the same time. But then if you say you increase that number to 100,000 people and your infrastructure is built for only 1,000 people, you might be in for some smelly and quite disgusting problems with your plumbing if you don't upgrade your infrastructure. And the same thing holds true for the data centers. If you want to be able to handle people with faster internet speeds, you need to upgrade your own internal internet speeds and switching and routing so you can handle all that extra data that's going to be coming through there. So the last couple things I want to touch on here, because we are definitely way longer than a normal episode, but I think that's okay. I hope that's okay with you all too, is fiber and DAC cables. So real quickly here, fiber cables or fiber optic cables are essentially of a different way of sending the Ethernet data. So the copper cables, the twisted pairs, those send the data through electrical signals, whereas fiber optic cables use long strands of glass filaments, and then that data is transmitted through shooting lasers through the glass filaments. And then each pulse represents either a 0 or a 1, which I think kind of the idea of shooting lasers through a cable for transmit data is pretty darn cool if you ask me. But because of this, and it's not doing electrical signals and it's shooting light, it's able to do a lot longer distances, and it's able to do it much faster as well without as many repeaters as you would need to do if you're running just standard twisted pair RJ45 Ethernet cable. And again, because on the Dark Assassins podcast, we actually care about context. As I mentioned with the CAT cables, those generally can do up to 100 meters. Fiber cables can typically do 80 to 100 kilometers. Yeah, so a lot more. So rather than 100 meters, 100 kilometers, without having to have the signal amplified. So this is why fiber is ideal whenever you're trying to do any kind of long distance cable run. It's basically the go-to. It's generally more expensive when you're talking distances that long, but it's a lot better because you don't have to add a bunch of repeaters and all that stuff. Now, generally, at least modern fiber cables are pretty resilient, but also the fact that there's glass inside, you potentially could break your cable. So if you are using fiber optic cables, you definitely want to be more careful with them than you would with just standard Ethernet, copper cables, because you technically have the potential to break the fiber optic cable. And then I guess another thing you'd want to make sure if you're dealing with fiber optic cables is you want to make sure the ends of the fiber optic cable are either covered or somehow can't get dust on them, because if you somehow get dust on that sensor that the laser shoots through, you're obviously going to have a bad time if it can't, shoot the laser properly and transmit the data. So that's also something to keep in mind. And then as we kind of mentioned when we talked about SFP, the way you plug these into a network switch is through an SFP transceiver, specifically for the fiber optic cable, which essentially allows the data to be transmitted into, those light flashes through the lasers, so it can actually, transmit and receive the data. Now moving on to DAC cables, or direct attached copper cables. In my opinion, this is you can kind of think of this as sort of a hybrid, between your standard copper RJ45 Ethernet cable and fiber optic cable. Now, it's not a perfect one-to-one, and it's not really in the middle either, but it has some similarities with both. So like the copper Ethernet cable, it uses a copper cable rather than fiber optic cable. So obviously, because of that, the distances are going to be limited. But unlike the CAT cables And similar to the fiber optic cables, it uses special SFP transceivers on them. But unlike the fiber optic cables, these are like built in directly to the cable itself. So you don't have to worry about buying, the separate SFP transceivers. Now, the biggest downfall with DAC cables is how short your runs are with them, which, unless your use case for using a DAC cable is, say, connecting your server to your switch in the same rack, you essentially have no use for DAC cables because they're essentially limited to 10 meters. And if you have network speeds of over 100 gigabits per second, it's more like 5 meters. So unless you're routing cables within the same rack, DAC cables are not going to be the way to go. But if, like I said, if you are only, doing runs within the same rack, then it's generally not that big of an issue. So this was definitely a long one and very jam-packed. And I know there was a lot of data that flew at you, both in terms of the data being streamed to your device as well as me saying data to you, but I hope you at least got something out of it. And if you enjoyed this episode, I ask that you would leave a rating and review and subscribe to the Dark Assassins podcast if you haven't done so already. And be sure, especially on this one, to share with a friend or family member who you think would like to learn more about networking and how the infrastructure of how the internet works, and all the good stuff that goes in to making the internet functional. And if you have any questions about this episode, since I know we covered a lot, so I wouldn't be surprised if there's questions or if I might have missed something, please either send me an email at contact@darkassassinsinc.com if you have any questions about this episode or topics you want me to cover in future episodes. And the link for that, the email is also in the show notes below, so you can just click on it there. So that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bool nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.